okay, I mean, there is this title, you know, applications are promised and so on, as always. But actually, I'm going to talk a bit more about some specific idea, which I think is very different, about how to achieve quantum advantage. But the kind of overall topic is related to spectroscopy, specifically to nuclear magnetic resonance spectroscopy. If you're not familiar with this is something that is done every day in basically every chemistry or pharmaceutical lab, where people create new molecules. And then what you want to do is you want to know, did I really create the molecule that I wanted to create? So, you know, you have it in some liquid, you put it into a nuclear magnetic resonance device, you measure a spectrum. That is done by shining microwaves onto kind of your vial. And then you get some kind of microwaves out, which you resolve by the frequencies that you get out. And then you get a spectrum of this form. And what would be really super practical is if you had some really good way of saying, this is the molecule I believe I have. What should the spectrum that I get out of this molecule be? And the reason why this is not straightforward to calculate currently is that if you would want to calculate the spectrum exactly, you would need to solve a quantum mechanical problem. But for us, as people who want to do something cool on a quantum computer, actually, this type of quantum mechanical problem is extremely beautiful, since actually it's a problem where you have to time evolve a state of coupled spins. And I think you all know that spins are exactly equivalent to qubits. So in some sense, it's a really direct thing where the problem you want to solve maps in a super obvious way to the quantum computer. So it's a really nice problem, very directly connected to quantum computing. And so from the application side, in some sense, the goal would be to say, okay, you have a molecule, you generate this type of Hamiltonian that describes, you know, the coupling of the nuclear spins. And then you calculate the spectrum. There are some additional interesting features to which I will come about the fact that you see in this spectrum, you know, various resonances. These are the peaks. They also have a width. And this width comes from specific effects, which I will address. But this is basically the application. But now, actually, I want to switch gears and use this topic, you know, kind of creating or calculating the spectrum for a spin system to talk a little bit about quantum advantage. I think we all understand that the major thing that needs to happen in our field is that we achieve quantum advantage for an application. Quantum advantage itself has been shown. And when I may say quantum advantage, I mean what also is called quantum supremacy, where the quantum computer does something that cannot be done with a classical computer. And this has been done for abstract sampling problems, which I think is already really important and a very important benchmarking steps for the devices that we have. Earlier this year, there was also a paper on some very abstract learning task that was maybe in the advantage regime. But it's very clear that we need more cases where we achieve applications that are closer, where we achieve quantum advantage that are closer, or where we achieve quantum advantage for something that is closer to an application. And I and many others believe that the topic where we will do this is for a topic where we solve intrinsically quantum mechanical problems. For example, calculate a spectrum for NMR. And before I continue with my work, I just want to shortly address the key method that currently dominates this idea of solving quantum mechanical problems, for example, calculating properties of molecules. And the method that is basically used for almost everything currently on noisy intermediate scale quantum computers, that is variational approaches. I think there's no need to recap this too much, but yeah, variational approach means you initialize your quantum computer, you act on your initial state with some gates that are parameterized, and then you measure at the end something, and whatever you measure, you minimize it by changing the gates that you apply. And this approach is very nice to get something done, to see that the quantum computer does something, to get something out that kind of makes sense. However, I think there's really a critical need to start doing something else than variational approaches. I mean, they have been studied, the progress is slow, we know there are fundamental problems like barren plateaus, the depth of the kind of number of gates we have to apply to get something reasonable scales in a way that makes clear that it will not work on noisy devices. And connected with the fact that you have barren plateaus, we have way too many measurements drawing out the time to kind of really converge a variational approach. So that said, of course, you know, they are nice. We also sometimes use them. And what's really missing is an alternative approach. And so that's where I want to talk about, or what this is about, an alternative approach to solving quantum mechanical problems. And to think about this, let's first now make a step back and say, okay, for kind of what case do we have provable exponential advantage of a quantum computer? And we have provable exponential advantage if we want to time evolve an initial state. So we do not have it if we want to minimize something or find a ground state or whatever, but we have provable exponential advantage for time evolution. So then what we should say is, okay, let's prepare some initial state and time evolve this. And now, of course, the issue is we need to be able to time evolve something and get all relevant properties that are interesting for a user out purely from a time evolution. And here is actually where a problem like nuclear magnetic resonance again comes in, because actually this spectrum is in some sense the Fourier transform of the time evolution. Yeah, what you really do also in experiment, and that's also what you would do on a quantum computer. You prepare a trivial initial state, you kind of push it out of equilibrium, then you time evolve it, and that is the non-trivial part. Yeah, you have a non-trivial time evolution, and then it kind of goes back into the trivial equilibrium state. And I mean, the time evolution is clear, but in like standard quantum computing, this kind of going back into the trivial equilibrium state is of course not included. But actually, if we think about NISQ computers, we quickly realize that that is already in our device. You know, even the equilibration that corresponds to nature is already there because the devices are noisy. And this is actually the major thing HQS has been working on, to simulate open quantum systems like nuclear spins of a molecule using quantum computers. And I will motivate this a little more in a second, but let me now also show you what the major, let's say, kind of scientific step is that we did to analyze noisy quantum computers and be able to map problems like nuclear magnetic resonance to a noisy intermediate scale quantum computer. The key goal was to say, okay, we know what the quantum computer is supposed to do. Yeah, we have some Hamiltonian, it should time evolve a number of qubits under a certain kind of setup using a Trotter algorithm and so on. So we know kind of what we want to do with the quantum computer. We then look at the quantum computer and say, okay, each of these qubits has various noise properties and so on. And we now run all these kind of gates and make this time evolution and so on. And now we want to have, given that the quantum computer is noisy, we want to have a certain simplified description of the whole thing that tells us what is the noisy quantum computer really doing. And we derived this in the form of what we call the noisy algorithm model, where you time evolve something, or the algorithm which you use is a Trotter algorithm for time evolving under Hamiltonian HS. You look at your quantum computer with all the noise in there, and then what you see is at the end you can write down an equation like this. And people who are familiar with this is like the standard description for open quantum systems. It's like the master equation in Lindblad form. And then again you have a closed form description that you can say, okay, now all the gates, all the time depends, everything is gone. Now we have a closed form description that helps you understand what is the quantum computer actually doing. And if you're interested in this, we actually have a paper on the archive on this, and instead of remembering the kind of reference here, you can also just search for my name, Marthaler, on the archive. You will find the paper, and actually we have implemented this whole procedure also in our cloud, where you can, for example, say this is the Hamiltonian I want, these are the noise properties of the qubits, and the thing spits out the effective noisy algorithm model that describes the whole time evolution. And so then the idea is, okay, we know the quantum computer is basically an open quantum system. We have things in nature that are open quantum systems. Yeah, everything in nature, a molecule, in that case, the nuclear spins of a molecule, are also coupled to some environment. The quantum computer has its noise coming from some environment. And so what we should always do is kind of map the open quantum problem from nature to the quantum computer, which is intrinsically an open quantum systems anyway. And there are intrinsic questions or very interesting questions that arise once you do this. So once you think about this in this way, what you realize is actually the power of using your quantum computer as an open quantum system could be higher than just using it as a closed quantum system, since for a closed quantum system, you just have to look at the time evolving the state. For an open quantum systems, you have to look at time evolving the density matrix. That means, the problem complexity has been squared. This is one way to look at it. The other, actually, but at the same time, once you look at open quantum systems, additional approximations become available that can solve this problem also on classical computers. Let me come back also to this point and say we actually have shown, or we have a method that interpolates between a quantum computer at strong noise, where you can simulate the quantum computer in linear time. So if you have n qubits, the time to solve any problem on the quantum computer scales like n, if the noise is very strong. But we can also show is as the noise on your quantum computer kind of gets smaller, the effort to simulate your quantum computer scales like 2 to the 2n. And here I want to come back to nuclear magnetic resonance. If your spin problem in your nuclear magnetic resonance is indeed an open quantum system, and it is, and you would solve it using a quantum computer using about 30 spins, and your noise is at a reasonable strength, meaning you have a problem that scales like 2 to the 2n, then think about it. It's like 30 spins. 2 to the 2n is 2 to the 60. That would be a problem already. That would be clearly in a quantum advantage regime, halving roughly the number of qubits you would need to achieve quantum advantage. And this is actually what we are aiming for in the near future. And currently we have a look at the existing hardware to see where it would be best to implement this in the near future. Thanks. With this, I'm at the end. Thank you for your attention. And we still have enough time for questions, if there are some.
We do indeed. Any questions from the audience? Yes.
Thanks for the talk. It was very interesting. So you mentioned how equilibration is built into quantum computers already because they're noisy. Naively, I would expect that equilibration of a quantum computer just kind of brings you to the maximum mixed state. Like it's not just the equilibration to some thermal equilibrium of a Hamiltonian you're interested in, but it's sort of catastrophic, wipes out all signals. Yeah. So how do you control that?
So this is actually a key point if you would, for example, try to do something like NMR, where going to this trivial state is fine. So your completely mixed state is the equilibrium state in NMR. Yeah? So that is why that is particularly good. We have other attempts where we want to go to an equilibrated state. a non-trivial equilibrium state, and that is indeed extremely difficult. And what you have to do is you have to use additional ancilla qubits as a kind of thermostat, yeah, to kind of force it into kind of thermalized state. Yeah, because otherwise you're correct. Because you do all the gates, yeah, and they kind of mix the noise in some sense to bring it to an equilibrium state. But then, if you don't want this, you have to assign, in some sense, additional qubits as a thermostat.